Going to start with series inverter topic, which I've covered briefly, but the audience were not enough. There were less students there. So let me revise what is inverter. So what does inverter do? So basically, they will convert DC signal into AC signal. So that is what they do, right? So can the next question is, can your SCR be used at when the input is DC? Can it be used? Yes, but the SCR has to be forced to turn off, right? And this technique of forcing to turn off is called as force commutation. Okay, and commutation means that to turn off some device. And basically, what do you want to turn off is SCR, right? So series inverter use SCR. That means there should be some provision for this SCR to turn off. Now, why do we prefer SCR still? Since we have a IGBT or a power BJT or a power MOSFET. So all of those later devices doesn't support high power application. It's meant for low to medium power applications, medium, high power applications. But SCR is the one which will support very high power applications in the greater of 100 kV, like 10,000 volts or 5,000 volts, something like that. Whereas IGBT and other devices, other power devices won't support that. That's why we are still preferring SCR, even if the input is DC. Now, if we are using SCR, we require commutating components. Now, in series inverter, this commutating components are LNC, right? So, LNC stands for inductor and capacitor. So, in a series inverter, your commutating components are permanently connected in series with the load, which is usually R. All right. So let us check out the circuit of basic series inverter. So this is the circuit of basic series inverter. I'll encourage you all to draw this diagram while I explain it to you. All right. So what do we have over here? We have input DC, then we have SCR T1 and SCR T2, and then we have LNC, which I have highlighted in yellow color, which is my commutating elements, which will turn off the SCR, basically help in turning off the SCR, and my load is the resistive load. All right, and these are the voltages written over here: VT1, VT2, VL, VC, and V out. V out is same as your voltage across the resistor. So this is my basic series inverter. Okay, and why it is called as a series inverter? Because the commutating components are connected in series with the load. So that's why it's called as a basic series inverter. I hope you have noted down this diagram.
Second, sir.
All right. So, meanwhile, while you're noting down the diagram, can you tell me what could be the immediate drawback of the circuit, looking at the circuit itself right now? Anyone can tell me what could be the possible drawback? From a okay, I'll let you know. From a brief perspective, let's say that your T1, okay, T1 and T2 both are on. So what will happen if both are on? Can T1 and T2
Short,
both can? Yeah.
short circuit. It can create a
Yes.
spark.
Yeah. It will create a spark and basically damage the voltage source as well as the SCR. And we are dealing with high voltages. We are not talking about 100 volt, 200 volt. We are talking about 1000 volts. All right. So there cannot be even a slightest possibility that T1 and T2 can be turned on simultaneously. That will lead to a dead short circuit. That's the limitation of basic series inverter. Is this clear to you? Okay. Yeah. So the series inverters operate at a higher switching frequency. So, I mean, in the range of 500 to 100 kilohertz. So that's why the size of LNC component which are required over here are small. All right. And LNC and R are selected in such a manner that it's an RLC underdamped circuit. Right. Now, what do you mean by RLC underdamped circuit? Zeta should be less than 1. That means R should be less than twice upon square root of L by C. Okay. That's what we have studied in underdamped systems, You know there are three types of system: critically damped, underdamped, overdamped. So when it is an underdamped system, what will happen is this will be the nature of current flow. It will the amplitude of the I out, I mean the in current will keep on diminishing. Okay, so your L and C are chosen in such a manner that the series RLC circuit forms an underdamped circuit. Is this clear about it? Now, can you tell me when does an SCR turn off? What are the two methods by which SCR can turn off? Okay, anyone? So what are the methods of turning off an SCR? Can anyone try? How can we turn off an SCR? What are the two techniques to turn off an SCR? Number one is you reverse bias it. That means whenever SCR is reverse bias, so SCR, sorry, I don't have the pen today with me at home. SCR has to be reverse bias, meaning cathode to anode voltage or anode to cathode voltage should be um, negative. Second technique is SCR can be turned off if its anode current is less than the holding current. Okay, this is method number two. So either you make the SCR reverse bias or you make the anode current less than the holding current. Is this clear to everyone? Yeah, please confirm by responding.
Yes, sir.
Okay, so in this nature of current, in this waveform which you see, at t equal to t1, you see over here the current is becoming 0. That means if it is becoming 0, that means SCR must be turned off over here. And that's the advantage we will be using this. So at such point where the current flowing through the SCR becomes 0 or less than holding current, it will turn off. Alright, so based on this, we'll go to mode 1. So we know that it's a RLC circuit, so it will produce a underdamped oscillations like this. But only first period is enough. First period will have proper amplitude. Next period onwards, the amplitude will go on diminishing. Okay, and we require such first period only. So in mode 1, what do we do is we keep T1 on, T2 off, and we have a RLC circuit over here. All right. So what will happen? Since we have a RLC circuit, we will have a underdamped oscillations, and the I out current will keep on rising, and then it will reach a peak like this. I out current will start increasing. It will reach a peak, and then it will go to near to 0 because it is following this nature, underdamped nature of current, right? So it becomes 0 at point X. All right. So what happens over here is SCR1 is triggered on to the on state. T off is off still. So I out current will build up, right? Inductor will store the energy, capacitor will store the energy. And as the circuit is underdamped, the load current decays. The load current is I out, will decay to a level 0 at point X. So what happens at point X as I out is 0, and it tends to reverse, right? Its tendency, normal tendency is to reverse, as you can see over here. The nature of the current, after it crosses 0, it will go to negative. But over here, as soon as it goes to 0, the SCR turns off. So at point X, as the I out is 0, it will tend to reverse, and SCR T1 is turned off. All right. And when this happens, in this case, what is my input current? My input current is same as my load current. All right. So if I check the waveform over here, I trigger the SCR number 1 over here, right? So 2 is not triggered yet, 2 is off. So it starts building up, current starts building up, reaches a peak, and then it decays down to 0. As soon as it reaches 0, your SCR will turn off. So SCR will turn off at point X. Is this clear to you? And the same is the nature of input source current, IN. Is this point clear? Yeah, any doubts up till now?
So IIN में why it's not going bill? Why the current graph is not going below the origin in IIN?
Below the origin means
I
negative.
mean, yeah,
Why? How it will go negative? If T1 is off, na?
yes sir.
T1 becomes off at point X. So T1 becomes off मतलब क्या? ये open circuit हो गया ना? Open
हाँ,
circuit हो गया तो where will ion flow? It will
नहीं
go to
करेगा
zero.
फिर.
So it will go to zero. That's what I'm saying. This is mode number one. So in mode number one, the current starts from zero, reaches peak, and it goes to zero at point X. And at point X, your SCR number one is off. Now what happens is we don't trigger SCR2 immediately. We trigger after a delay, let's say. Okay. So there is a delay here from year to year. Okay. So from year to year, we are not triggering SCR T2. We give some time because in reality, practically, SCR will take some time. It's called as a turn off time of SCR, right? When you study gate switching characteristics of SCR, then you will understand that SCR takes some time to turn off. All right. So after a delay, we'll then trigger the SCR number two. So what will happen as long as this period is there between X and Y? Anyone can tell me? So between
The
X
S,
and Y,
the T1 is off.
yes, yes. In X and Y, your T1 and T2 both are off. Okay. So because T2 is not triggered yet, T2 is actually in the forward blocking mode. It's capable of turning on, but it's not turned on yet because I mean we have not applied the trigger pulse. So remember from the previous cycle, your capacitor was charging, and this will hold the charge VC. So this VC will make the T2 forward bias, but is not triggered on yet. Okay. So what will happen? In will be zero. Even I out will be zero in this case. So as shown in the waveform between X and Y, there is a zero current, and in is also zero. So this is mode 2 operation. Is mode 2 operation clear to you?
Yes sir.
Quickly tell. Okay, fine. I hope you all are following.
Sir, in I out I have one query that when it is going in negative, the wave is going in negative direction. Is it because the SCR2 is on, right?
I'm going to teach that next.
Okay.
Okay. So next is mode number 3. As you can see in mode number 3, T1 is completely off now, and the T2 was in the forward blocking mode, and now we applied the gate trigger. As you can see in the waveform, the green color gate trigger is applied. Now the current, how it will flow negative. Why negative? As you can see over here, the positive is considered to be top to bottom when the current flows from top to bottom. So any current flowing reverse now will be considered as negative. So here my capacitor was holding that charge, and now it has a discharge part. So capacitor charge is released now via the T2 part. Okay, T2 is turned on. So the current will flow like this. If you remember correctly over here, if you can check it out, IN is still zero. Why? Because T1 is off. Is that all right? Okay. So in mode 3, T1 is off, T2 is on, and your I out current flow is negative. All right. It starts from zero, it goes to a negative peak, and then it decays again to zero. Here like this, from Y to Z. And again, what happens at Z? Again, the load current becomes zero. I mean, the current load current becomes zero, and the SCR T2 turns off. All right.
Sir.
Yeah, everyone. Okay. So here is some relation between I out. Let's say I out is actually sine omega t. Then voltage across the capacitor will be cosine, right? So your voltage across the capacitor is actually proportional to cosine. So in a half cycle, the VC will reverse the polarity, as you can see, because sine and cos reverse the polarity after 90 degree. Okay. So the capacitor in mode 3, lot of interesting stuff is happening. First of all, the current is becoming negative. T1 is off, as in IN is 0. Capacitor is discharging, and it discharges to a negative peak, and then it again decays back to 0 because of underdamped condition. Here, this nature it will follow. So this part of the waveform from Y to Z, input current will be 0, but I out current will be negative. And then again from Z to A, you don't turn on T1 still. Why we don't turn on T1 immediately? Because every SCR will take some time. Will take some time, let's say TQ time to turn off. And then TQ time might be in microseconds, but still it will require some time. So you should never immediately trigger the next SCR. Always said should be some deadband period where the current is 0. So again from Z to A, none of the SCRs are conducting, and I mean the current is 0, and as same as your input current is also 0. Then again at point A, your SCR number 1 is re-triggered, and the cycle will continue.
So that is why that because as you said, if there should not be an immediate turn of SCR2 after the SCR1, that is why there is a it is slightly when it goes from positive to negative, there is a halt in between.
That's the reason why. That's why it's not a pure sine wave. You don't get a pure sine wave in power electronics practicals, actually, in practice, because there will be some distortion associated. And depending upon what power device you use, this turn of time will differ. Okay. So T off time, capital T off is the time in which none of the SCRs are conducting. So this one complete period, T, capital T, is the underdamped oscillation period, this period. Okay. So over here that we call it capital T. And T by 2 is, I mean, this is including that T off period. Okay. So there is a conducting period for the SCR, and then there is a T off period where none of the SCRs are working. So from Y to Z, we have mode number 3. Then again, mode number 2 will carry on. Then again, mode 1 will be happening. Okay. Now, one thing is there, you can ask this question. I will ask this question from yourself only. So, why does the positive peak and the negative peak are symmetric? What's the reason for that? Anyone?
Because it is because actually there is a since there is a gap between the turning off on and on of SCR, and immediately it cannot be because immediate turning on off can create a spark, so due to the delay it looks symmetric. That's what I feel.
No, no. I'm asking why does the I out peak and the I out negative peak and positive peak look similar? The reason is in the mode number 1, the capacitor charges, it stored charges, right? In mode number 3, it releases the same amount of charges. So that's why. That's why they are symmetric. So here I've written positive half current is same as the negative half of current, right? So as the capacitor stores charges during one half cycle and releases same amount of charges during the next half cycle. ऐसे खाली theoretical है, practically we will get slight deviation between the two. Okay, so this is the working of, and as you can see clearly, the output current is AC current. So what are we giving over here? Input is a DC and we got a AC current. Now this AC current is flowing through the resistor. So how will be the nature of V out? How will V out look like? Exactly the same nature, same wave shape as I out current. All right. Why? Because it's a resistor. Resistor means there is no phase difference between current and voltage. So the wave shape will be same. The nature of the waveform will be same as I out. Is that fine? So it's not a pure sine wave. It's slightly distorted. You have this extended period over here wherein the current is 0. So similar distortion will be there in the V out waveform. So this is the working of your basic series inverter. It's a very important topic from inverters. As you can see, inverters weightage in the entire syllabus is the highest. So this is quite important topic also. Is this clear? Any doubts in this? Immediately let me know so that I can, move on.
So just as you were discussing about that, why do they look symmetric? Just can you show the mode one क्या होता है और mode three क्या होता है?
This is mode
Mode
1
one. Okay.
and this is mode 3.
अच्छा, so they are opposite.
Of course, they are opposite. In mode 1, capacitor is charging. In mode 2, it is discharging. Okay, can I proceed?
Yes, sir.
So from this waveform, this circuit will also lead to some two numericals, which we have to solve today. So let's begin. Now T off, actually dekhoge, so T off is included in T by 2. So T by 2 minus T off, I will show it to you over here. T off is called as the circuit turn off time or a dead zone time. So please write these equations now. T is called as the period of the damped waveform. So T by 2 is actually, there is some period over here which they have marked in the output. From Y to Z, they are calling it as pi by omega d. And from A to this point over here, right, including the dead zone region, it's pi by omega. Matlab T by 2. Pi by omega is actually T by 2, capital T by 2. And capital T by 2 minus T of is pi by omega d. Are you following? Understood the difference between the two? Yes?
Yes.
Okay, fine. So from here, T by 2 is actually pi by omega d plus T of, where omega d is called as the damping frequency or the ringing frequency, which is given by this formula, omega naught into 1 minus zeta square, where omega naught is 1 upon square root of LC, and zeta is, you know, zeta square will be r square C divided by 4L, the whole raised to half. All right. So omega d or omega r, that is damping frequency or ringing frequency, are one and the same. So it's given by the formula 1 upon LC minus R upon 2L the whole square raised to half. So please note down this formula. If you take this square root of LC inside, you will get this formula. Okay. Please note down this formula. This will be used in the numericals. All right. So if this is the case, T by 2 is pi upon omega d plus T of. So what will be T given by? T will be given by 2 pi upon omega d plus 2 T of. So you know the frequency of the inverter frequency will be 1 upon T. So it will be given by this equation number 1.2. Please note down this equation number 1.2 also quickly. Have you noted down? Okay. So here the inverter frequency will be 1 upon 2 pi upon omega d plus twice T of. All right. So these two formulas are required for the numericals solving. Okay. Next is, what are the drawbacks of this inverter? So the one drawback is that T2 cannot be triggered before T1 is turned off. In short, both the SCR cannot be turned on simultaneously. If that happens, then it will lead to a dead short circuit. As you can see, there is a dead short circuit if both the SCRs T1 and T2 are turned on simultaneously. And this is a major drawback of a basic series inverter. Also, another drawback is the source current input flows only during the positive half cycle. Okay, so let us go back to waveforms and understand this. So as you can see, I in is the source current, and as you can see, it only flows during the positive half cycle. because in a negative half cycle the T1 is, because of T1 being off, the input is disconnected. Okay, so that's another drawback. The input source current is only present during the positive half cycle. Also, the maximum operating frequency is limited because omega is less than omega r. All right. So here it is from the waveform. Again, you can see over here, omega. Your omega should be less than omega d. Okay. So that's the problem which we face, limited maximum frequency. Also, the load current and the voltage waveform gets distorted due to the dead zone, right? So as you can clearly see, this we have discussed, it's not a pure sine wave. So there is a dead zone in the output voltage waveform and the current waveform. So output voltage waveform and current waveform both will be the same nature. But I out, for I out, what will be the peak value? V out upon R, 1 minus V out upon R in the negative direction. The negative current peak will be minus V out upon R. Positive current peak will be V out upon R because it's a resistive load, as you can see. All right, so that's another drawback. And the last one is that the commutating components, that is LNC, have to carry the load current continuously, right? In both mode number 1 and 3, the current is continuously flowing through the commutating elements, that is LNC. Therefore, high ratings are for them are necessary. Okay, let me show it to you. This is mode 1. So as you can see, mode 1, the load current flows through LNC in mode 1. Now let's go to mode 3. And you can see mode 3 again, the same load current, maybe in the opposite direction, but it's flowing through LNC, commutating components also. Okay, so LNC have to be a very high ratings because continuously the current flows through them. So this in short are the working, the waveforms and the basic equations for a basic series inverter along with the drawbacks. Now I'll wait for your questions. If you have any question you can ask, or else we can proceed. I hope you have noted down these equations because this will be required in the numerical, which we are going to solve next. I'll pause here for 30 seconds so that you can ask something if you are not understood. Any questions? Anyone? Okay. So I hope you have followed this topic. Now we'll move on to the numericals next. This was about the basic series inverter. Now we'll go to the numerical based on the basic series inverter. Okay. So let's begin with the numerical on basic series inverter. Every numerical which I have done in power electronics is important and you cannot miss that. Please practice every numerical we have solved together in the class. Okay, including today's and in the future I will be teaching, covering some more numericals. So this numerical is about calculate the output frequency of a series inverter with L, C and R value given, 6 millihenry, 1.2 microfarad and 100 ohms, and T of period is 0.2 millisecond. Okay, so you have to calculate the output frequency for a series inverter. If did not mention anything, it means basic series inverter. Now that is first part. Second part is, if the load resistance is varied from 40 ohms to 140 ohms, find out the range of output frequency. Okay, can someone confirm? Y'all can hear me still?
Yes, sir.
Okay, so please note down the parameters R, L and C and T off. And this is first part. Second part, में the R is changing from 40 to 140 instead of 100 ohms. Okay, so let's begin. Now we know the formula for T. It's a very, very simple, application over here. T application of formulas which have been discussed before. So T is 2 pi upon omega d plus 2T of. Now omega d formula is 1 upon LC minus R upon 2L the whole square, the whole raised to half. So you have the value of L, you have the value of C, then you also have the value of R. Substitute in this formula and let the calculator do the calculations for you. So please someone check whether the value is around 8.33 into 10 is to 3. It will be radians per second. Omega is unit is radians per second. So the strategy is first to calculate omega d and then substitute in this formula to calculate capital T, and from capital T you can calculate frequency, inverter frequency. That is 1 upon capital T will be inverter frequency. Completed? Please cross check the values. Okay. Are the values matching with what you are calculating? T will be coming around 1.154 milliseconds, and 1 upon that will give you around 866 hertz. The inverter frequency is 866 hertz. Is this the value you are getting? Please immediately tell.
Yes, sir.
Okay, okay, yeah. Okay, you were there last time, Aditya. Yeah. So, okay. In the second part, now we got the value of F, the output inverter frequency. Now we'll put the value of R as 40 instead of 100, and put the value of R as 140 instead of 100 again, and recalculate the value of frequency. So what is the strategy? When R is equal to 40 ohms, calculate the frequency. So for calculating the frequency, again you have to recalculate omega d. Put all the values R, especially R over here. So let me increase this. So here you put the value of R as 40 and recalculate the value of omega d. Put it in this formula and you will get the value of F, inverter frequency. Now in the second case, this you can do it on your own. In the second case, when R is 140 ohms, substitute the value of R as 140 ohms over here, and then again substitute you will get a new value of omega d, put it in this formula and calculate the value of F. So as you can see, if the value of R is increasing, the frequency is reducing. And here in first case, the value of R was smaller, the frequency was higher. So here you get the range of output frequency when the resistance changing from 440 to 140 ohms will be, the output range will be 239, around 240 hertz to 1046 hertz. Is this clear? Is the numerical clear to you? Any doubts?
Resistance and frequency are inversely proportional to each other, right? So,
In this case, it is appearing so. You decrease the resistance at the frequency is increasing. It is appearing so from the formula. All right. So can we go to numerical number 2? Okay. So next numerical is about again the basic. We have discussed single phase basic series inverter, that is called a single phase. Um, Single phase inverter is operating, actually I should have written series inverter. So single phase, actually it's a series inverter. I might have missed out on that, because if you call single phase inverter, it can be a parallel inverter also. So it has to be a series inverter. Let me add that value over here. In a single phase series inverter, the operating frequency is 50 kilohertz. So we have been given operating frequency. That is your inverter frequency is 50 kilohertz. Then we have SCR turn off time. Now this is something new. This we have not discussed so far. SCR turn off time. It's a new parameter we have been given. RLC value is given and Vin is given. And the question is to check whether the inverter would operate. Now how to check whether the inverter will operate? Anyone can tell me? When inverter will not operate. So inverter will not operate if your T of time over here is less than your less than what? Your turn off time of your SCR. If that happens, then your SCR, your inverter won't operate. So let us check that condition. Okay, let us check this condition. So for this, we have to calculate the value of omega d. So frequency is given as 50 kilohertz. So omega will be 2 pi f. 2 pi into 50 kilohertz. 50 k radians per second. The omega d formula is 1 upon LC minus R upon 2L the whole raised to half. So substitute the values of L, C and R, and you will get omega d close to 0.04 into 10 raised to 6 radians per second. You can check it out later on. Now, what is the circuit turn off time formula? It is same as the time of the dead zone. So T off will be pi upon omega minus pi upon omega d. Now you will say, sir, we have not discussed this. Yes, we have discussed already. Now from this waveform, if you see carefully, what is T off? T off is nothing but pi by omega minus pi upon omega d. Alright? So that's the same formula we are using over here. Pi by omega minus pi by omega d. Now omega and omega d we have already calculated. So put in over here in the expressions. So you'll get the value of T off as 21.46 microseconds. Okay? So we can conclude that as the T off time is more than the SCR turn off time, which is around 10 microseconds, the series inverter will operate normally. When it will not operate normally? When T off time is less than the SCR turn off time. Meaning SCR is not turned off and you are turning another SCR on. So in that sense, it won't work. Is it making any sense? Are you following? Understand the question properly, please. Is this clear to you how to solve this numerical? You have to just calculate omega d and omega. That's it. Very simple task. Two formulas are there. Here we are using 1 and 2 formulas and we are getting the result. So such type of numerical can be asked for 5 marks in the exam. So please expect numericals also in the paper. And my recommendation is please solve. Don't miss out on any numerical which we have solved till date in the last 39 lectures. All right. Everyone has completed? Hello, can someone confirm? Did you get these values?
Yes, sir.
Okay, all right. Next we will talk about basic series, modified series inverter. Now, this is the circuit of modified series inverter. So before that, what we will do is, we will see why we are studying this modified series inverter. The problem in the basic series inverter was T1 and T2 cannot be turned on simultaneously. What will happen? If that happens, it will lead to a dead short circuit, right? And which will damage the input supply also, or it will also damage the SCRs. So it's not safe. All right. So this drawback can be removed by making this kind of arrangement. As you can see, this is SCR number 1, SCR number 2, and this is one inductor only, but we have taken the tapping from the middle. All right, we have taken the tapping from the middle. So left hand side of the inductor part is called as L1, right hand side is called as L2, and this is capacitor C, resistance R. So we take the output across the resistance R, and input is my DC. Okay, so this is the modified series inverter with coupled inductors. So they can ask you this question: explain basic series inverter, mention its drawback, and draw a circuit which will remove the drawback of the deadband condition. Okay, so this is the modified series inverter. Can we start with the working? Have you noted down the diagram? L1 and
Yes,
L2
sir.
are, yeah,
Just a second, please.
L1 and L2 are exactly the same value. So what's the beauty of such a connection? If an voltage has been induced in L1, same voltage will be induced in L2 because of mutual exclusiveness. We can see the dot, right? So same voltage, if VL1 is induced in L1, VL2 will be induced in L2, which will be same as VL1. So this is my modified series inverter. Okay, so which all drawbacks it is addressing? So this circuit will overcome the drawback of limited. It will remove the drawback of limited operating frequency. What do you mean by limited operating frequency? Your omega was less than omega d. That means you cannot increase this value greater than omega d a lot, right? And the second drawback was there is a dead short circuit of V in observed by the time when both the SCRs are turning on simultaneously. So this drawback will be addressed and somewhat reduced. I mean, the second one will be completely eliminated, the drawback, and the first one will be somewhat in operating frequency range you can increase. All right. So it consists of two SCRs, one inductor with a center tapping, a capacitor, and R, and the input supply. So voltage is taken across R, load resistor. So let's begin the analysis. So what was the problem happening? It has the same waveforms, same waveforms as your basic series inverter. All right. So what was the problem? Let's say T1 is triggered. All right. And let's say we trigger T2 over here. So this is the triggering point for T2. What will go wrong? Or what can go wrong over here? I out current has not reached 0 and you are triggering T2. So basically in a basic series inverter it will lead to a short circuit because temporarily both the SCRs are turning on simultaneously. Matlab, this T1 won't turn off until it reaches point X. Until it reaches point X, it won't turn off. That means now if you trigger T2 at this instant of time, your I out current is not 0. So it may not be less than holding current. That means your SCR is still on and you're turning on another SCR. So it should not lead to dead short circuit. So that is the drawback which we are addressing now. So let's say your T1 is triggered. So I out builds up. it reaches a positive value and decays towards 0. Now let's say that because of this VL1 voltage is induced across L1. Alright. Now since L1 and L2 are mutually coupled, VL2 voltage will also be induced across L2 like this. Alright. Now let's say I out is nearing 0. I out is nearing 0 but it has not reached 0. And we have triggered T2 now. Okay. So what should happen if you trigger T2 now? T2 has been triggered by the gate pulse. So T2 is on now. So now let us calculate the KVL. Let us calculate the VT1 voltage at this condition, at this instant of time when T2 is turned on. So in this loop, if you go, you will have like this. We have to go right. So you will have minus plus minus V in plus VT1 plus VL1 plus VC plus I out into R equal to 0. Now your capacitor voltage is charging up till V in. So capacitor voltage is nothing but V in. So V in and V in gets cancelled out. So VT1 will be equal to minus VL1 minus I out into R. So from here it's clearly visible that your VT1 is negative. Alright, it has been reverse biased and therefore it turns off. So that means by turning on T2, T1 is automatically turning off because of voltage across it. Is it clear? So as soon as you turn on T2, there is no danger that T1 remains on. It will turn off immediately because this VT1 is coming highly negative. So it will reverse bias T1 SCR and it will turn it off. Is this point clear to you? This is very, very crucial. If you understand this, the next part will be very, very simple. All right. Any doubts in this? So again, I repeat what we have done so far. T1 has been triggered on, right? So current is building up. And before giving the time for the current I out to reach to 0 or point X, T2 is triggered on. So that means momentarily T1 and T2 are on. So what happens over here? Because of voltage being induced, VL1 and VL2, and if you apply the KVL over here, you will soon find out that VT1 turns out to be negative. Now if VT1 is negative, that means the voltage across the anode to cathode is negative in a SCR. So it will reverse bias and it will turn off immediately. So this shows that when T2 is turned on, even before I out reaches a 0 level, your T1 gets turned off. And that is how the problem of dead short circuit is solved over here. Alright. Now, this T2 voltage, this T2 which is on, is also forward biased by VT2 voltage. Now you can apply the KVL in loop 2 and find out that VT2 is positive. That means VT2 is in the forward conducting mode also. That means you can apply the trigger pulse at any instant of time, even without waiting for the I out to become 0 when T1 is on. Okay. As soon as your T2 is on, your T1 will be off automatically. Okay. So next, it is also solving the dead short circuit problem. So what was happening in a basic series inverter? If T2 has been turned on before the current in T1 vanishes, there will be a dead short circuit which will destroy the input source. And this drawback in a modified series inverter, there is no such danger. Okay, this is the modified series inverter. There is no such danger. If one is turning on, other will be automatically off. If T2 is turning on, and T1 is turning on again same time, T2 will be turned off. So no two SCRs are turned on simultaneously in this case. Okay. So also this feature will permit the inverter to operate at a frequency higher than the ringing frequency. So earlier what was happening, omega D was less than omega, but in this case omega D can be more than omega. So in that way, your omega can be much greater than omega D, sorry. So that means you can operate at a much higher frequency. So that high frequency operation drawback which was there in basic series inverter is also addressed over here. Alright, so this is the working of modified series inverter. Any doubt anyone in this? Then we'll discuss the last topic for today, that is will be parallel inverter. Any doubts? Please
No,
let me.
but how come that? Because in the original series inverter, since it was, how could there is a possibility that accidentally two SCRs could turn on, and in this case both SCRs can't turn on?
So here in previous case, if accidentally T2 has been triggered, see T1 and T2 are triggered at the user command. We triggered and on. So let's say if T2 has been triggered on over here, in the meanwhile the current flowing through the SCR has still not reached zero. That means T1 is on and T2 is triggered on. That means there will be a dead short circuit. Okay. In this case, this is allowed. This is possible. Even if T1 is on and its current is not reached zero, T2 can be triggered. So as soon as your T2 can be triggered, that's what I'm explaining. So as soon as your T2 is triggered on, because of the voltage being negative at VT1, it will immediately turn off. That's what the equation is telling you, right? So now T2 is on and T1 is also on. But T1 being on, your VT1 becomes negative immediately under these conditions. And once the VT1 immediately turns negative, your T1 turns off immediately. मतलब हो क्या रहा है? You're turning on T1, then you're turning on T2 before T1 turns off. Now if you turn on T2, your T1 will become automatically off because of the structure of the modified series inverter. As you can see, it's clearly evident from the KVL also that VT1 is becoming negative. And VT1 negative means T1 is turning off. Is your doubt clear?
Yes, sir.
And same thing can happen over here. Let's say that ये T2 बंद होने की जगह we have turned on over here. Here we are turning on T1, right? So let's say T1 is turned on here only. T2 बंद नहीं हुआ है. T2 is on only, and T1 has been triggered. So same thing will happen. Your T2 will automatically turn off once T1 turns on. So at no point of time both the SCRs are on. So that will prevent the dead short circuit. All right. So this is all about modified series inverter. Any more queries? Any doubts in this? All right. I'll move to the last topic of the day. I guess I cannot cover commutation topics right now. Maybe tomorrow one time I will allot and cover all the commutation circuits for SCR, because I think these topics are also important. So that's why I am more focusing on them also. Okay. Now, uh, focus all your attention in the parallel inverter because it's again a very important topic. Everyone, just 10-15 minutes more and then we are done for today's topics. We will be discussing single phase parallel inverter. This is okay. This is your circuit of single phase parallel inverter. You have to listen and concentrate fully to understand this thoroughly. Can we begin?
Yes, sir.
Okay. So what do you see over here? You see a DC over here. Input is DC source. Let me highlight it. So input is DC and we are expecting that this inverter output will be AC. That's what the inverters are, right? With a frequency. Here L is connected in such a manner that the current which is flowing, IN. Now you will soon find out that even the load current flows through this L. So what the L property is, L doesn't like the current to change, so it will maintain it constant. So basically the job of this inductor L is to maintain the current flowing through it is constant. It will not change it. Then we have two SCRs T1 and T2, and then we have a commutating capacitor C, which will, with the help of which if one SCR is on, other will turn off. If T2 is on, T1 will turn off, and if T1 is on, T2 will turn off. And this kind of arrangement is called as class C commutation. We will be discussing commutation circuits tomorrow. So this is class C commutation. All right. What do you mean by class C commutation? One SCR can turn on at a time, and that is called as complementary commutation, which means if T1 turns on, T2 will be off. If T2 turns on, T1 will be off. All right. So far understood the connections properly. See, the normal problem or mistake people do is connect V in over here, which is wrong. V in is connected at the center tap, at the central winding, exactly at the center of the primary winding. So this is my primary winding. It's the output transformer, right? Oh, it's looking like a 10. This is primary winding and this is secondary winding. N1 is to N2. That's a turn ratio. All right. So this is my DC. Again, I'm repeating, the negative part of the DC is connected at the center of the primary winding. So we have a secondary winding. What's the property of the transformer? Whatever voltage appearing across the primary, it will appear at the secondary. Correct? Yes or no? So can we begin with the working? Okay, now please concentrate. So we are in mode number 1 and we are considering the time less than 0. So what do we do is we turn on T1 transistor. So T2 is not triggered yet. T1 transistor is turned on. So the current will start flowing. The current will flow from inductor, positive terminal of V in, inductor T1, SCR T1, then the upper half of the primary winding. Then it will not flow through the lower half of the primary winding. Then it will flow back to the minus V in. All right. So that is what will happen. Again, I repeat, the current will flow from inductor T1, upper half of the primary winding, and back to the minus V in. So this I out, this current is I out, because this current will be mutually induced in the output also. So in the output, the there will be a current I out because of the transformer, and the turn ratio is 1:1. So whatever current over here is in the primary upper half, same will be appearing across the output load. All right. So again, here we can see there is an inductor, so current will slightly build up, and that inductor will store the energy in this period, in this point of time. So this current will be mutually induced across the secondary winding, and you will have a I out current. Remember, it's just the upper half of the secondary winding. If we consider both the halves, then it will be like the current also will be flowing, but the magnitude of current will be different. Is this clear? So due to this, what happens is, listen carefully. Are you listening? Okay. So due to this, what happens is, this V in voltage appears across the upper half of the primary winding, and due to mutual exclusiveness, your EMF is induced in the lower half also. So here in the upper half we have V in the lower half also we have V in. Due to this, as you can see, capacitor is connected in parallel with the primary winding. The capacitor voltage can now charge up till -2 V in. The capacitor voltage can now charge up till -2 V in volt value. All right. And since T1 is on, this positive voltage will appear at the anode of T1, T2, and this negative voltage will appear across the cathode of T2. That means T2 is eligible to turn on now. So that means T2 is in the forward blocking mode by capacitor voltage. Is this point clear? Hello?
Sir.
Yes, sir.
Okay. So far so good. Alright. So what has happened? T1 is turned on and the current is flowing through the upper half of the primary winding. Due to this, volt EMF is induced across the upper half. Similarly, in the lower half also EMF is induced because of the property of this windings, mutually exclusive windings. So the capacitor voltage can charge up to 2 V in now. All right. So now let's go to, now since I out is been flowing through the load, there will be a voltage. Okay, I out is flowing through the resistive load, so nature of the voltage across V out also will be similar. Okay, now let's go to the next mode, mode number 2. We are considering time equal to 0 now. So now what is happening is T1 was on, okay, and we just turned on T2 because now it has become eligible to turn on. All right. So as soon as your T2 is just turned on, what will happen now? Actually, this is wrong. This should be V in.
It will spark.
Spark nahi, पहले सुनो तो सही. What will happen is, instead of, now what will happen is entire capacitor voltage will come appear across the T1. And V into very, very high value, it's 500 volt, let's say. So entire minus 1000 volt will appear negative or reverse bias across T1. So which will immediately turn it off. Which will immediately turn it off. Did you understand this? As soon as T2 turns on, the voltage across the capacitor will come in parallel, negative mein, because this is the anode of T1, this is the cathode of T1, SCR T1. Alright, and a negative minus 2 V in voltage is been applied. So what it will do? It will immediately turn off T1 transistor. So T1 transistor is off now. But still the current should be in the same direction because of the inductor. So now the current will flow like this. It will flow through T2. It will flow through the lower half of the primary winding and back to minus V. Is this point clear? Is this point clear to you?
Yes.
Okay. So same way, I out current will keep on flowing. All right. So this is your mode 2 at time t equal to 0. Remember the sequence of events. Huh? Now we'll again go to mode 2, next part. Okay. So just time greater than 0, or it is between t1 and t by 2. All right. So now what was happening? T1 is off, T2 is on, and the current was flowing through T2, lower half of primary winding and back to minus V in. But at the same time, your capacitor is now discharging. पहले charge हो रहा था, right? Now it is discharging. So it will discharge via upper half of the winding and lower half of the winding. So the current should be continuous. Na? Matlab, if there is a current, it's an inductor only, right? This primary and secondary coil are inductors only, right? The current cannot suddenly vanish, right, from the upper half of the winding. So the capacitor current will flow through the upper half, and lower half में क्या करेगा? Lower half में earlier there was no current, right? So this current IC and this current I out will balance out, such that the condition is similar to when it was t less than 0. Okay. So the capacitor will now discharge. So here I have written over here I out to maintain I out in the first winding and 0 in the second winding. So now this is what will happen. So capacitor is discharging now. It is discharging. It will continue to discharge. So now what will happen? Now because of this, minus V in voltage will appear across here. See the connections how they are made. This positive is been connected over here. And then we have negative. So plus minus V in direction has reversed. So because of this voltage being induced in the lower half of primary winding, upper half of primary winding will also induce a voltage minus V in. I mean this Vn. So this minus Vn and this minus Vn will appear in parallel with capacitor, right? So now capacitor can charge up till minus 2 Vn. All right. So this capacitor can charge up till minus 2 V in. Now T2 is on. All right. Now this voltage will appear across T1. So now T1 is not on, huh? It's eligible to become on now. So this voltage plus 2V in will make sure that T1 is in the forward blocking mode now. Are you following? But now see the direction of change of I out. I out direction has changed. Now it is going into the dot. As you can see into the dot over here. So this current also will flow into the dot. Earlier what was happening? Current was flowing out of the dot. Here it is flowing out of the dot, right? Here it is flowing into the dot. So this I out current will become negative and V out also will become negative. Is this point clear? Very, very crucial. Yes, no. Immediately tell.
Yes, sir.
Yeah. So in first case, in mode 1, I out current was positive. Here it is negative. That means you have a AC current again. The story is still not over. So now T1 is in the forward blocking mode, meaning you can turn it on. So let's see. Actually, this PDF was very big. So I have divided into two parts. So in the first part, I have explained up till here. Now let me open another PDF. So you all can also refer it like this. Now this next PDF part, we will explain the third part. So now what was happening? Since T1 is eligible to turn on, we turn it on. And we turn it on, right? So what will happen when we turn on T1? Immediately across T2, this entire minus 2V in voltage will appear in the reverse way. So T2 will be off as it is reverse biased by the capacitor voltage. Okay. And now the same story will repeat. Again, the current will flow from L, T1, upper half of the secondary winding, of the primary winding, and back to minus V in. Again, we have got to the same state as we have started. Is this clear? And this will make this to happen. All right. Again, the voltages will be induced and the capacitor will charge up till plus minus 2 V in, and the story will keep on repeating. Is this clear? So when T1 is on, I out will be positive. When T2 is on, I out will be negative. Any doubts in this? Here there is a polarity, I have to check it out. Can we check the waveforms now? Okay. Yeah, these are the waveforms now. Can you see them all together? Hello?
Yes, sir.
Okay, this is at time t equal to 0. Remember I told you there is an inductor connected over here so that the current is constant. So I out current is constant. Okay. So here you see whenever a particular thyristor is on, the current flowing through it is constant. That's why it is connected over here. So IT1 and IT2 is very simple to draw. Now, let's consider the case t equal to 0. So before t equal to 0, क्या हो रहा था? Before t equal to 0, we are in mode 1. And what is there in mode 1? Mode 1 mein your T1 was on. Alright. So VT1, whenever a thyristor is or a SCR is on, the voltage across it is 0. Correct? What about the voltage across the capacitor? It was plus 2V. You remember? Plus 2V. And then what about output voltage? Why output voltage is V instead of 2V? Anyone can tell me? Why output voltage is V instead of 2V when the capacitor voltage is 2V? Can anyone answer this question? The answer is really simple. The turn ratio from whole primary to secondary is 2. See, what we were saying, upper half of primary. That voltage is V and that has been transferred. I mean, that is the voltage which we get. But there is upper half. If we combine both upper half and lower half, then the turn ratio will become 2. That means the load voltage will be half of the amplitude of the capacitor voltage. So at this point of time, the capacitor voltage is minus 2 V in. So output voltage will be minus V in. Are you getting the point? So V out nature will be same as VC nature. What is the difference? Instead of 2 V in we have V in, instead of minus 2 V in we have minus V in. Alright. So now what happens? Now we enter into mode 2. So mode 2, what will happen now? We have triggered T2 on. So when we trigger T2 on, the capacitor will discharge and will reach minus 2V in value. As soon as it reaches minus 2V in value, the T1 transistor is off. So it will hold that voltage. Alright. Output is negative as we have discussed. The capacitor current will be reducing to 0 at this point, and at this point T2 is turning on. So as you can see marked over here, T2 being in pink in color. So as soon as your one transistor is turning on, the current flowing through it is constant, IT2, that will be I out. Alright, in first case it was I out over here for T1. Now next, what is happening in mode number 3? In mode number 3, again the capacitor voltage is rising from minus 2 V in to plus 2 V in. Over here we have triggered T1 on. Alright, and as the capacitor voltage reaches 2 V in, your output voltage has also reached plus V in. And during this point now, your T1 has triggered on. So this capacitor voltage will hold on that value until we trigger T2 on. So as soon as we trigger T2 on, again the capacitor voltage will fall down and the cycle will repeat itself. And here you can see this is the output voltage and that is the AC voltage. So we have started with the input DC and now we are getting output AC. So that's how we get, that's how this parallel inverter will work. It's slightly tedious, here and there we have to look it out, but that's the way the waveforms are. I've already told you all, IT1 and IT2, whichever transistor is on, just draw a constant voltage, constant current of constant value. Alright, and VC nature is same as V out nature, and this is the voltage across VT1. Any doubts in this? You have to study this. I will be providing these handouts to you by today in some time. So you can check it out and let me know if there are any more doubts. So if there are no doubts, then we'll stop the lecture now. Because I thought series and parallel inverter was important and you all should study that, I've covered this topic again. So next lecture will be tomorrow. The timings I will give it to you. Okay. Tomorrow you all have anything in the college or online? Offline. You all are going to college for any
Sir,
reason?
mostly I will be for some temporary time. Mostly I will be like till 1 or 2 in the college.
Okay. No. I'm proposing that can we keep it in the afternoon, 6 o'clock or so?
Sir, 7 chalega.
Acha, 7 to 8 I should keep. Okay, fine.
Yeah.
So tomorrow I will cover the commutation circuits. Yeah, let me turn off the recording now.
Sir, tomorrow
Tell
at